Hello everyone. In this video I'm going to be talking about annihilators, which are basically linear differential operators that, when performed on a function, turn it into zero, right? Annihilate it. And going over several examples, but before I get to these examples, I want to talk about some basic rules of annihilation and general rules like what differential operators annihilate what functions, and there's some pretty basic functions: polynomials, exponential functions, trigonometric functions, and that's really it for this video. All right, so remember our hopefully this notation looks familiar from maybe previous reading. But these are our differential operators. Just some examples. So when you see this capital D, it means the derivative with respect to whatever the independent variable is. It doesn't have to be x, could be t or whatever else you want. And so you see D, it's derivative of blah with respect to x or t or whatever the independent variable is. D to the kth power is just performing the derivative k times, so this really represents the kth derivative of some function with respect to the independent variable. Alright, and so what we mean by annihilates, say d to the nth here, annihilates any of these functions: y equals 1, x squared, x cubed, all the way up to x to the n minus 1. Some quick examples of this: if y were just x, right, d squared applied to the function y equals x, this should become 0, right? And you can kind of do this, say this is the same thing as applying d to x twice, and we apply d to x, the derivative of x with respect to x is 1, and then apply d again, derivative of 1 is 0, and this is what it means to be annihilated. X is annihilated by d squared, right? It becomes 0. All right. So that's what all these annihilates means. All right. So yeah, d cubed would annihilate 1x and x squared. D to the fourth would annihilate 1x, x squared, and x cubed, etc. Right, so d to the nth annihilates everything from 1 up to x to the n minus first power. Right? This is for polynomials. Okay, and then this here, this d minus alpha, where alpha is a constant, d minus alpha to the nth applied to some function annihilates the following all the following functions: e to the alpha x, where this is that same alpha here, x times e to the alpha x, x squared times e to the alpha x, all the way up to x to the n minus 1, right, 1 less than this power of n here, x to the n minus 1 times e to the alpha x. And again, a quick example off to the side here. If I just say, let's apply d minus 2 to the function, y equals e to the 2x. All right. So again, you treat these operators almost like polynomials, really, and this is apply d to e to the 2x, and then subtract 2 e to the 2x and see what happens. Now if I apply d to e to the 2x, that's derivative of e to the 2x with respect to x, that'd be 2 e to the 2x, and then minus the 2 times e to the 2x, and you see that we get 0, right? So e to the 2x is annihilated by d minus 2, to the first power. And d minus 2 squared would annihilate e to the 2x. It would also annihilate x times e to the 2x, and I'll leave that to you. D minus 2 cubed would annihilate e to the 2x, x e to the 2x, and x squared e to the 2x. And I can keep going with this. All right, I don't have a lot of room for examples here, so I'm going to kind of just state this. This crazy rule here. Again, I'd recommend memorizing these things just to make things quicker for you. The operator d squared minus 2 alpha d, so again, alpha is a constant, plus, and then another constant, alpha squared plus beta squared, where alpha and beta are numbers, constants, to the nth, annihilates all the following functions. E to the alpha x times the cosine of beta x, where that alpha and that beta are here and here, right? And then, multiply these by any power of x up to x to the n minus 1, right? One less than this power on the operator. And all those will be annihilated by such an operator. And same thing involving sines. So e to the alpha x times the sine of beta x, and then times any power of x up to n minus 1. Those also will all be annihilated by such an operator. And again, I'll do an example later where we verify something like that. All right, then a couple rules that'll be useful in the examples I have. Number 4 here. If L is some linear differential operator, that annihilates y1 and y2, then that same operator L will annihilate any linear combination of y1 and y2. Right, so some constant times y1 plus some constant times y2. And then one final very important rule that we need to know about annihilators, about linear operators. So suppose L1 and L2 are linear differential operators. If L1 annihilates y1, function y1, and L2 annihilates y2, but they don't annihilate the others, so L1 doesn't annihilate y2, L2 doesn't annihilate y1. Well, if that's the case, then the product, right, if you multiply those operators, apply the product of those operators, L1 times L2, that will annihilate the linear combination, any linear combination of y1 and y2. All right, and I'm going to be using these last two rules quite a bit. Okay, so some examples. Right, and in every single one of these examples, I have the following instructions. I'm asked to find a linear differential operator that annihilates the given function. All right. And really what I'm going to try to do here is find a linear differential operator of the smallest order that annihilates the given function. All right. Okay, so so the function here, y equals 1 plus 6x minus 2x cubed. Right, this is a linear combination of the following functions, right, of 1x and x cubed. And from one of the previous rules I put up earlier, these are just powers of x. So and the highest being x cubed. So the differential operator of the lowest order, of the smallest order, that would annihilate all these, is d to the 4th. Now, of course, d to the 5th, d to the 6th, d to the 7th, any higher order would also annihilate these. But like I said, I'm trying to find differential operators of the smallest order, lowest order, that actually, that annihilate the function. Right, and as was stated in that, rule number 4 I wrote, if we know of an operator that, annihilates several functions, that same operator will annihilate any linear combination of those functions. So d to the fourth will annihilate, take the fourth derivative of 1, 0. Fourth derivative of x would be 0. The fourth derivative of x cubed would be 0. And since d to the fourth annihilates all three of these, it will then therefore annihilate this function. So d to the fourth of this 1 minus 6x minus 2x cubed, this is annihilated. And so the linear operator in question then is d to the fourth. And you can verify this by simply taking the fourth derivative of this function. Right, so y prime, right, would be 6 minus 6x squared. Y double prime would be negative 12x. Y triple prime would be negative 12, and then you have that's a constant, and you see how the fourth derivative is indeed 0. All right, so applying this operator d 4 times to this function annihilates it. Okay, let's get into another example. I'm going over several of these. All right, so this one is the function y equals 1 plus 7 times e to the 2x. All right. Now, I know from earlier rules that I wrote that just the plain old d to the first, that operator, the first derivative, d annihilates the 1, right, that term. And this e to the 2x, we saw earlier, d minus 2, right, this operator, d minus 2 to the first. This, oops, can't spell. This annihilates just e to the 2x, and therefore, any multiple of e to the 2x. Also, d does not annihilate e to the 2x. And you can check that, right? So this annihilates 1, but it doesn't annihilate e to the 2x. And you can check that, right? The derivative of e to the 2x is 2 e to the 2x, not 0. And d minus 2 applied to the constant 1 does not annihilate it, right? Because this would be the derivative of 1, which is 0, then minus 2, which is not, equal negative 2, which is not 0. So I have, like in my fifth statement, right, the fifth rule I wrote up earlier, if I have two operators, say L1 and L2, so d and d minus 2, one of them annihilates one function, 1. The other one annihilates another function, e to the 2x, but they don't annihilate the other ones. D doesn't annihilate e to the 2x, d minus 2 does not annihilate 1. Well, then their product will annihilate any linear combination of these. So if I want to annihilate the linear combination, 1 times 1 plus 7 times e to the 2x, I need the product. So by rule 5, the product of these operators, d times d minus 2, will annihilate 1 plus 7 times e to the 2x. This will be equal to 0. All right, so the operator we're looking for, the L, is d times d minus 2. And let me verify that. All right, let me actually show you that indeed this operator annihilates the function in question. And you can just apply them. Right now it's factored. You could distribute. You could say this is the same thing as d squared minus 2d and apply that. So if I took the second derivative, and the first, d represents like the first derivative, d squared represents the second derivative. First derivative of this function would be 14 e to the 2x. The second derivative of this function is 28 e to the 2x, and then I apply this operator to them, we'd get 28 e to the 2x minus 2 times 14 e to the 2x, and that indeed is 28 e to the 2x minus 28 e to the 2x. That is indeed equal to 0, right? So it is annihilated by this operator, d times d minus 2, or when multiplied out, d squared minus 2d. Same thing. Okay. Next example. So like I said, I'm going to just do a bunch of these and keep applying these rules I've stated at the beginning of the video. All right, so another one where we're asked to again find a linear differential operator that annihilates the given function. All right, so again, I have multiple terms. X, right, d squared annihilates x, and then this x times e to the 6x would be annihilated by d minus 6 squared. All right, going back again up here, d minus 6 squared would annihilate everything from e to the 6x up to x times e to the 6x, right? So I'm seeing this x times e to the 6x there. This annihilates x times e to the 6x, d minus 6 squared. Also, d squared doesn't annihilate, right? D squared does not annihilate x times e to the 6x, and you can very easily verify this. Take the second derivative of x times e to the 6x with respect to x, you'll see that that's not 0. And the d minus 6 squared, this does not, when applied to x, is not 0 either. This would actually end up being you can multiply this out. This is d squared minus 12d plus 36 applied to x. Now the second derivative of x is nothing, sure, but then you'd have negative 12 times the first derivative of x is 1. So negative 12 plus, this ends up being negative 12 plus 36x, which is definitely not 0. So again, I have a scenario like the previous example where I have these operators that, they annihilate one of the terms, but they don't annihilate the other one. So then by that rule 5 again, their product, right? Their product, d squared times d minus 6 squared, this would annihilate x plus 3x e to the 6x. This should be equal to 0. All right. So there's the linear operator we're looking for, d squared times d minus 6 squared. All right. And again, I want to verify this. I'll do it for the first several examples, the verification. Now you can apply d minus 6 and then d minus 6 again and then d again, right? Just do all these ones. Again, if you were to multiply this out, this would end up being d to the 4th minus 12d to the 3rd plus 36d to the d squared. All right. So what I need to do to is take the first derivative, second derivative, third derivative, fourth derivative. All right. So I'm actually gonna do first derivative y prime would be 1 plus, and then the product rule here would be 18x e to the 6x plus 3 e to the 6x. All right. And I'll just pause it and come back here when I'm done with up to the fourth derivative. Okay, so I'll leave this to you to verify, but I've taken the first derivative, second derivative, third derivative, fourth derivative of this function. Took a little bit. And then substituting into this, basically you get the fourth derivative minus 12 times the third derivative plus 36 times the second derivative, and you can use a calculator or whatever and verify that this is indeed 0. Again, I'll leave that to you. So I have this fourth order linear differential operator, and that's the smallest order possible. You could multiply this by, make a d to the fifth, d to the sixth. You can multiply it by any higher powers of d, but this is the smallest order differential operator that I can find that will annihilate this function, turn it into 0. Okay, let's go again. Alright, so same instructions. This time it's just plain old trig function. Alright, again, all my examples here will simply involve polynomials, exponentials, and trigonometric functions. Alright. So this cosine, 2x is the same thing kind of as like e to the 0x times the cosine of 2x, if you think about it that way. So the value of alpha being 0, the value of beta being 2. Back in this rule that I wrote. Alright, these ones involving the trigs, they have alphas and betas, but again, e to the 0x, cosine 2x is like alpha is 0 and beta is 2. And there's no power of x in front, so we're just focusing on this guy, and our operator would be d squared, minus 2 times 0d, so no d, plus, and then 2 squared. So the operator that annihilates this is d squared plus 4. Simple as that. D squared plus 4 applied to the cosine of 2x would annihilate it. All right, so the linear operator I'm looking for is d squared plus 4. And again, if you'd like to verify this, just take the second derivative. Y prime would be negative 2 sine of 2x. And then the second derivative would be negative 4 cosine of 2x. And then popping these in, this is just, applying, it's the second derivative of cosine of 2x, so it'd be negative 4 cosine 2x, and then plus 4 of it, right? Plus 4 times the cosine of 2x, and you can hopefully now see that this is indeed 0, annihilated, right? So d squared plus 4, that linear operator, does indeed annihilate the cosine of 2x. Okay. This next example kind of combines rules 4 and 5 that I had written up earlier. Yes, there are 3 terms, but these 2 terms, right, 13x and 9x squared, right, this is a linear combination of x and x squared, right, and both of these, x and x squared, are annihilated by d cubed. Right, so I have one operator that can annihilate 2 terms. And then this sine of 4x, it's just like the cosine of 2x in the last example. You could think of this as e to the 0x times the sine of 4x, so alpha is 0 again, beta is 4. This term, sine of 4x, would be annihilated by the operator d squared plus 16, right? D squared plus 4 squared. And again, you can verify that. And then you could also go through and verify that d squared plus 16 does not annihilate 13x plus 9x squared. And d cubed does not annihilate sine of 4x. But they do annihilate, the terms separately. So their product, d cubed multiplied by d squared plus 16, this would annihilate, I'll put just y here, alright, so I don't have to write all that again. This would annihilate this function. Alright, so the linear operator I'm looking for here is d cubed times d squared plus 16. The annihilator of that function. Or if if you put the d cubed inside, as d to the fifth plus 16 d cubed, and if you wanted to verify that this indeed annihilates this function, go up to the fifth derivative, plug it in, plus 16 times the third derivative, and you should get 0. And this time I'll leave it to you if you want to verify that. All right, it's got a couple more. This one here, again, this first term would be annihilated by, all right, I'll just put annihilator. The annihilating operator for e to the negative x would be d plus 1. Right, that'd be d minus alpha, where alpha is negative 1 here. And then these two terms, you see how there's x e to the x and then x squared e to the x? We're going back here. X e to the x, x squared e to the x. Well, the value of alpha is just 1 there. Those would be annihilated by the following. Right? Their annihilator would be d minus 1, right? Because alpha is 1, is both e to the x terms. And we're going up to power of x on these is up to x squared. So that'd be d minus 1 cubed. That would annihilate both these terms, because this would annihilate x times e to the x. This would also annihilate x squared times e to the x, and therefore would annihilate any linear combination of those two, which these last two terms are. All right. And then you can check for yourself that d plus 1 would not annihilate these two terms, and d minus 1 cubed would not annihilate e to the negative x. So then their product would, though. Right? So d plus 1 times d minus 1 cubed of y, applied to y, would be annihilated, would annihilate y, would make that 0. Okay, so the linear operator I'm looking for here is d plus 1 times d minus 1 cubed. Now, again, you can leave this as is and apply d minus 1, d minus 1, d minus 1, and then apply d plus 1, and hopefully you see 0. Or you could multiply this out like some polynomial and get basically a polynomial in these d's and find whatever derivatives you need to. This would be a fourth order differential operator. So you'd go up to the fourth derivative and plug in all the derivatives after multiplying this out and verify that you get 0 again. And again, I would leave that to you to verify. All right, then I have one last example. So again, two terms this time. 3, the constant, is annihilated by just d. That would annihilate 3. This e to the x times cosine of 2x. Now this time alpha is 1, right? That's e to the 1x, and the beta is 2, right? It's cosine 2x. So based on, again, the rule I put up earlier, the annihilator for this would be d squared, right? Remember, it's minus 2 alpha d, so minus 2 times 1d, so minus 2d. Then plus alpha squared plus beta squared, 1 squared plus 2 squared, which is 5. And there's no power of x attached to this, so it's just to the first power. Right, so the operator d squared minus 2d plus 5 would annihilate this e to the x times cosine of 2x. Right? And then, d would not annihilate this term. D squared minus 2d plus 5 would not annihilate this term. You'd be left with 15, right? 5 times 3. I mean, yeah, you'd have 0 here and 0 there, but then you'd still have 5 times 3. And so therefore the product would annihilate the entire function. All right, so d times d squared minus 2d plus 5, right? This operator applied to y would be 0. So the linear operator I'm looking for is d times d squared minus 2d plus 5. Or if you'd like, d cubed minus 2d squared plus 5d. And if you want to verify this, take the first derivative, second derivative, third derivative, and do the third derivative minus twice the second derivative plus 5 times the first derivative, and you'll see that you'll get 0. Alright, it will indeed annihilate this function. Alright, so lots of examples there. Again, hopefully, I would recommend memorizing these annihilators for your powers of x, your exponentials multiplied by powers of x, and your trigonometric functions multiplied by powers of x and exponentials. And that takes care of a bunch of different classes of functions that you can annihilate with certain linear operators, linear differential operators. All right. And hopefully watching me do these several examples helps you out when you're working on problems similar. And thank you very much for watching.